Have you ever had that feeling that underneath all the chaos of the universe, I mean, the insane complexity of matter, the sheer variety of life, the just seemingly random nature of human relationships, that there's some kind of hidden order?
Oh, absolutely. It's really the ultimate intellectual adventure, isn't it?
Yeah.
The search for those deep rules.
Right. And it's not an order you see by looking at the objects themselves, but it's in the rules of transformation that govern them.
Exactly. And that search, it led mathematicians to invent this single incredibly powerful concept. It's a structure designed not to study specific things like numbers or protons or even cousins, but to analyze the relationships.
The rules.
The rules that dictate how those things move, how they change, and how they interact, all while, and this is the key, maintaining their essential form.
And that concept, which sounds so academic and dense, but is actually the grammar of the entire universe, is group theory. It is, at its heart, the mathematical study of symmetry. So for today's deep dive, we are going on a journey to find the organizing principle that unifies everything. I'm talking from the structure of quarks at, 10 to the minus 18th meters, all the way to the complex sociological structure of a marriage system governing thousands of people on the other side of the world.
And this really represents a crucial shift in how we think. It's moving away from just studying quantity, how much of something there is, and moving toward analyzing structure.
And the power of group theory is in its ability to model invariance.
Invariance, that's the word, how a system maintains its identity, its core self, even while it's undergoing massive transformation or change. And the amazing thing is, any system, anywhere, satisfies the simple internal logic of a group. It instantly inherits the entire library of group theory theorems.
So our mission today is a true deep dive. We are going into the very axioms, at the four foundational rules of this structure, to reveal these deep isomorphisms, these hidden, shared logical patterns that link these radically different parts of reality.
We are going to unify the subatomic and the sociological.
With the same four rules?
Put simply, we are searching for the universal grammar of structure.
Okay, let's unpack this. Because before we can even begin to appreciate its universe-spanning applications, we have to master the simple, abstract internal logic that gives this thing its immense power. So what is the fundamental algebraic skeleton we're dealing with?
Well, the beauty of a group is its simplicity. It's conceptually sparse. It requires very little to generate immense power. So formally, a group is just a non-empty set. Let's call it G for now, and it's combined with a single binary operation.
An operation being just a rule for combining any two things in the set?
That's all. We usually write it with a little dot or an asterisk. It's just a rule that says how any two elements combine to form a third.
And the reason this abstract idea is so foundational is that any system, and it doesn't matter if the elements are numbers or physical rotations or, social classes, it just has to satisfy four fundamental rules, four axioms to be a group.
Precisely. And if it satisfies those four axioms, the entire logical structure of group theory, which has been developed over centuries, becomes instantly available to analyze that system.
Okay, so what's the first pillar? What's the first rule of the club?
The first axiom is closure. It's just the requirement that the set be self-contained under its operation.
So no escaping the system.
No escape. You take any two elements from the group, let's call them A and B, and you combine them using the group's rule. The result, A dot gay B, must also be an element of that same group.
It's a closed world. You can't combine two things inside the system and end up with something outside the system.
You've got it. I mean, think about the set of all integers under addition. You add 3 and 5, you get 8. 3, 5, and 8 are all integers. The system is closed.
Right.
But now take the set of prime numbers, and let's try to use standard addition. You take 3 plus 5, you get 8. 8 is not a prime number.
So the system broke. It's not closed.
It's not closed. So the set of prime numbers under addition is not a group. But in the physical world, think about the symmetries of a square. If you rotate it 90 degrees, and then you rotate it another 90 degrees, the result is a 180-degree rotation, which is still a valid symmetry of the square. You never escape the set of possible symmetries.
Okay, so closure locks down the system, defines its boundaries. What about the second rule? This one always seems a little tricky.
That would be associativity. And it dictates that for any three elements, A, B, and C, the order of grouping, the parentheses, doesn't change the final outcome. So A dot B in parentheses, then dot C, is the same as A dot, parentheses, B dot T73.
No, wait a minute. You said earlier we're going to talk about how the order of operations matters immensely. How can the grouping not matter? That feels like a contradiction.
It's a really subtle but vital distinction. Associativity isn't about the sequence of the elements. It's about the stability of that sequence. So imagine you're calculating the total effect of 3 sequential transformations. Associativity just ensures that if you calculate the effect of A combined with B first, and then combine that result with C, you get the exact same final state as if you calculated B combined with C first, and then combined A with that result.
So the sequence A, then B, then C is fixed. But it doesn't matter if you chunk it as ABC or ABC, the language is consistent.
The language is consistent. It's absolutely essential for defining the result of complex strings of actions, like when you're multiplying a bunch of matrices together in physics.
Got it. Okay, so we have a closed, consistent system, but what anchors it? What's the starting point?
That's the third axiom, the identity element. There has to be a unique element, we'll call it E, inside the set G, such that when it operates on any other element A, it just leaves A unchanged.
So E dot A is A and A dot E is A.
Exactly. It's the do-nothing operation.
The zero state, the baseline. What's its philosophical function in the structure? Why is it so important?
It provides an anchor point. It's an absolute state of no change against which all the other transformations and actions in the group are measured. If the elements are rotations, the identity is a 0-degree rotation. If they're numbers under addition, it's the number 0.
And without that baseline,
without that identity, you couldn't really define what change even means. And you certainly couldn't define the fourth axiom, which is maybe the most critical of all.
Which is the axiom of reversibility, invertibility.
Exactly. Invertibility states that for every single element A in the group, there must exist a unique inverse element. Let's call it A inverse, which is also inside the group.
Such that when you combine them, you get back to the start.
You get back to the identity. So A dot A inverse equals E.
So for every action, there's an undo button that is also part of the set.
And that is the crucial requirement. This is what separates groups from other weaker algebraic structures. A 90-degree clockwise rotation has an inverse. A 90-degree counterclockwise rotation, adding 5 has an inverse. Adding -5.
It means the system doesn't destroy information.
Right. Contrast that with, say, multiplication by 0 in the real numbers. Once you multiply a number by 0, you can't uniquely get the original number back. So there's no inverse. So that operation can't be part of a group structure. Invertibility ensures the system can always return to where it started.
So that framework, closure, associativity, identity, and invertibility, that defines the group. Now, let's get to the big one. The major consequence of how these elements interact, which is really the difference between a simple system and a complex one, the commutative question.
This mathematical distinction, whether the operation is commutative or not, is probably the single most significant factor in determining the kind of reality the group describes.
Okay, so a group is called a abelian if the order doesn't matter.
Right, named after the brilliant Norwegian mathematician Niels Henrik Abel. If the operation is commutative, so A dot B equals B dot A, it's abelian. Simple arithmetic addition is abelian. 2 plus 3 is the same as 3 plus 2.
But if the order in which you perform the two operations does matter, then it's non-abelian. If A dot B is not equal to B dot A.
And that non-abelian structure is. It's the mathematical signature of inherent complexity, of asymmetry.
The classic demonstration is just rotating an object, right? If I take this coffee mug and I rotate it 90 degrees forward around the x-axis and then 90 degrees sideways around the z-axis, the final position is totally different than if I did the sideways rotation first and then the forward one.
And that's not just a cute trick. That phenomenon is universal, from classical mechanics all the way to the quantum realm. That non-commutativity is why navigating a spacecraft is so hard. The sequence of burns matters.
And in quantum mechanics.
In quantum mechanics, the operators that represent two different properties of a particle, like its position and its momentum, are non-commutative. The order in which you measure them fundamentally changes the outcome. And that mathematical non-commutativity is the formal root of the Heisenberg uncertainty principle. Not at all. If the position operator, let's call it P, and the momentum operator, Q, were commutative, if P dot Q equaled Q dot P, there would be no uncertainty principle. You could know both perfectly.
It's astounding that the simple difference, whether two things commute, determines whether a system has fundamental limits on what you can know. Now, despite how abstract this all sounds, there's a theorem that brings it all back to something concrete.
Yes, that's Cayley's theorem. It's a truly profound insight. It states that every abstract group, no matter how weird, is structurally identical or isomorphic to a subgroup of a symmetric group.
Okay, let's make that accessible. What does it actually mean for you and me?
It means that no matter how complex the elements are, whether they're matrices or quantum states or rules of logic, at its core, every single group can be thought of as a group of permutations.
Just shuffling things around.
Just shuffling things, simple rearrangements of a set of objects. This is the bridge from pure algebra to concrete action. If the elements are numbers, the group is a set of rules for shuffling the order of those numbers. If the elements are social roles, the group dictates the possible, permitted ways those roles can be rearranged within the social structure.
It grounds everything in action and transformation.
Exactly. Cayley's theorem shows us that the concept of action is baked into the very definition of a group. And that allows us to transition from these abstract mathematical sets to the observable real-world transformations.
Okay, so that algebraic skeleton, as you said, has no bias. Let's now see how nature uses this structure, often, obligatorily, to build everything from the smallest subatomic particles to the largest crystal structures.
This is where we enter the domain of ontological group theory. And here, in physics, the math isn't just a descriptive model. The symmetry is the physical law. When physicists say they're searching for the fundamental law of nature, what they're really searching for is the underlying symmetry group of the universe.
And the most massive, most successful application of that idea has to be the standard model of particle physics.
The standard model is a towering intellectual achievement, and it is built entirely on the foundation of what's called continuous infinite groups, specifically Lie groups, named after Sophus Lie.
And the whole model is just a combination of these groups.
It is. The standard model mathematically describes the electromagnetic, the weak nuclear, and the strong nuclear forces through a single gauge theory, which is defined by a direct product of three Lie groups. G sub Sm equals Su3, C times Su2 times U1y.
Okay, that notation is pretty dense. Let's break that down, force by force. Let's start with the strongest one, the strong nuclear force, described by Su3.
Right. Su3c is the group that governs quantum chromodynamics, or QCD. This is the force that binds quarks together to form protons and neutrons.
So what does the 3 foot in Su3 mean physically?
The 3 signifies the three dimensions of the group, which correspond directly to the three color charges that quarks possess. We call them red, green, and blue. Quarks are constantly transforming between these three states according to the rules of this group.
And what about the force carriers themselves, the particles that mediate the force?
Well, the structure of the Su3 Lie group is generated by 8 fundamental mathematical operations. And those 8 mathematical generators correspond precisely to the 8 different types of gluons, which are the particles that carry the strong force. The math dictates the physics.
And we know this group is non-abelian. We said non-commutativity has massive consequences. So how does Su3's non-abelian nature show up in the real world?
This is the really revolutionary part of QCD. Because Su3 is non-abelian, the gluons themselves carry color charge.
So they interact with each other.
They interact with each other. This leads to the phenomenon of self-interaction.
Which is totally different from the photon of electromagnetism. The photon is electrically neutral, so it doesn't interact with other photons.
Exactly. And this self-interaction of gluons causes the strong force to behave in a very strange, counterintuitive way. At very, very short distances, the force is actually weak. Quarks can move almost freely inside a proton. We call that asymptotic freedom.
But as you try to pull them apart...
As the distance between quarks increases, the self-interaction of the gluons creates these color flux tubes, and the force actually increases with distance. It's like stretching an incredibly powerful elastic band. The further you pull, the harder it snaps back.
And this explains color confinement. It's why you can never, ever observe a single quark by itself.
It is the deep mathematical reason. The non-commutativity of the Su3 group is why quarks are permanently confined inside composite particles called hadrons. It is an inescapable consequence of the group's structure.
Amazing. Okay, let's move to the other two components, the ones that govern the electroweak interaction, Su2L cross U1y.
So this is the part of the model that unifies electromagnetism and the weak nuclear force. Let's start with U1y. It's the simplest one. It's an abelian group associated with something called weak hypercharge.
Abelian, so it's commutative.
It's commutative, which means its force carrier particle, which eventually becomes the photon we know and love, does not self-interact. And that's why electromagnetism follows the simple inverse square law and is long range.
Okay, so what about Su2?
Su2L is the weak isospin group, and it is non-abelian. It acts on pairs, or doublets, of left-handed fermions. For example, the electron and its corresponding electron neutrino. And that subscript L is hugely important.
L for left-handed.
Yes. It denotes the extreme inherent asymmetry of the weak force. It's called parity violation. The weak force fundamentally distinguishes between left-handed and right-handed particles. Its generators correspond to the W+, W-, and W3 bosons.
So we have this unified theory with an abelian group U1 and a non-abelian group SU2 working together. But in our world, the resulting forces look totally different. The photon is massless, but the W and Z bosons are incredibly heavy. Where does that difference come from?
That is the ultimate group theoretic drama of the Standard Model. It's the spontaneous symmetry breaking orchestrated by the Higgs mechanism.
So the symmetry was there, and then it broke.
In the very early universe, the combined SU2 cross U1 symmetry was perfect. All the force carriers were massless. But as the universe cooled, the Higgs field settled into a non-zero value, and that act spontaneously broke the symmetry.
What was the mathematical consequence of that breaking?
It caused crucial mixing of the mathematical fields. Specifically, the W3 boson from SU2 mixed with the B field from U1. And this linear combination produced two new physical particles, the massive Z boson, which mediates the neutral weak current.
And the massless photon.
And the massless photon. The familiar electromagnetic force we see every day is actually a broken remnant of a higher unified symmetry that existed only for a fleeting moment at the beginning of time. The mass of the W and Z bosons is a direct measurable consequence of this specific Lie group structure dissolving.
And this all flips our whole idea of what a particle is. Eugene Wigner's insight was that the particle isn't a thing. It's a behavior dictated by the group.
Yes. Wigner won the Nobel Prize for this. He offered this profoundly abstract definition. He said that elementary particles are defined as irreducible representations of the Poincaré group, which combines space-time symmetry and translations.
Okay, irreducible representation. What does that mean in practical terms for something like an electron?
Well, a representation is just a concrete version of the abstract group structure, like a set of matrices that follow the group's rules. An irreducible one is one that can't be simplified or broken down any further.
The most fundamental version?
The most fundamental version. And Wigner showed that these irreducible representations are classified by only two numbers that remain invariant under all possible symmetry operations: mass and spin.
So an electron isn't a tiny ball. An electron is the unique, fundamental way that the abstract symmetry group of the universe can be realized in spacetime. And it's identified by its specific mass and its spin of 1/2.
The particle is the symmetry behavior. The structure precedes the substance. That is the deep ontological claim.
Okay, that was the world of the continuous and the infinite. Let's apply the same logic to the tangible world, the solid world, where we find discrete symmetries in repeating patterns. Let's talk about crystals.
Right. In condensed matter physics, a crystal is defined by an ordered, repeating lattice of atoms. And that means it has to possess a specific set of discrete symmetries: rotations, reflections, and most importantly, translations.
And group theory gives us basically the periodic table for all possible crystal structures.
It gives us the classification theorem. The full symmetry of any crystal lattice is described by a space group, which combines the rotational and reflection symmetries of a single point with the translational symmetries of the repeating unit cell.
And the amazing result is that there's a finite number of them.
Exactly. Using pure group algebra, mathematicians prove that there are exactly 230 unique space groups possible in three-dimensional space. Not 231, not a million, 230.
That's incredible given the infinite number of possible chemicals and molecules.
It's a mathematical necessity. Because a crystal has to satisfy the closure axiom. A translation followed by a rotation must still be a valid symmetry operation. That combination imposes these severe constraints. And this finite, complete classification is incredibly useful for material science.
How so?
Physicists can predict material properties: conductivity, piezoelectricity, elasticity based purely on which of the 230 groups the material belongs to. The group tells you the properties.
Okay, so how does the internal structure of a group predict something like whether a material conducts electricity?
That links directly back to the translational symmetry of the crystal lattice. That perfectly repeating structure leads directly to something called Bloch's theorem.
And Bloch's theorem says what?
It's a statement that the wave function of an electron moving in a periodic potential, like a crystal, has to transform in a very specific way under translation. It's a direct group theoretic constraint on the quantum states of the electrons.
And what's the physical consequence of forcing the quantum wave functions to obey this group rule?
It creates the electronic band theory. The symmetry requirement dictates that electrons can only occupy specific, defined ranges of energy, the energy bands, and they're forbidden from others, the band gaps.
So whether a material is a conductor or an insulator is literally determined by the group theory of its crystal structure.
Absolutely. If the valence band is full and the energy gap to the next available band is huge, the material is an insulator, like a diamond. If there's no gap or the gap is tiny, electrons can move freely, and it's a conductor, like copper. The entire electronics industry is built on this group theoretic consequence.
Okay, let's zoom in one last time on the physical world, moving from these infinite lattices to individual molecules in chemistry using point groups.
A point group describes the finite symmetry operations of an isolated molecule. For example, a water molecule, H2O, has the C2V point group that defines 4 simple operations: do nothing, rotate by 180 degrees, and 2 different mirror reflections.
So it defines the shape, but how does the shape or the group define the function?
A huge one is chirality, or handedness. This is absolutely vital in biochemistry and pharmacology. A left-handed molecule might be a life-saving drug, while its right-handed mirror image is totally inert or even toxic.
And group theory gives you a simple test for this.
A simple, fail-safe algebraic test. A molecule is agral, meaning it's superimposable on its mirror image, if and only if its point group contains a specific symmetry element called an improper rotation axis.
And if that one element is in its group definition.
If that specific algebraic operation is present in the group, the molecule has no handedness. It's a chiral. If that element is absent, the molecule is chiral. Full stop. Its biological behavior is dictated by that simple property of its point group.
And chemists use these algebraic shortcuts to avoid doing impossible calculations when they're trying to predict how molecules interact with light, right, in spectroscopy.
Yes, it turns a massive quantum mechanical problem into a simple symmetry matching game. This is most clear in determining the selection rules for infrared or Raman spectroscopy. These rules tell you which of a molecule's many possible vibrational modes can actually absorb energy from light.
So how does the group structure tell you which modes are active?
Well, for a transition to be allowed, the symmetry of the vibrational mode has to match the symmetry of, say, the electric dipole operator. And by just looking at the molecule's character table, which is a little matrix derived directly from its point group, a chemist can instantly see the symmetries of all the possible modes and predict exactly which peaks will show up on their spectrum.
So you don't have to solve the incredibly complex Schrödinger equation for the whole molecule.
You just check a table of symmetries. You bypass the quantum mechanics with group theory.
Okay, this is where it gets really mind-bending for me. We've established this deep, necessary connection between math and the physical world. But now we're going to apply the same rigorous algebraic logic to something far less rigid, far messier: human culture, marriage rules, and the very architecture of thought.
Right now we transition to what we can call heuristic group theory. Here, the group isn't the ontological law of reality, but it's a powerful structuralist model. We use it to uncover the hidden, deep, invariant logic that lies beneath the apparent messiness of social customs.
The assumption is that these same kinds of algebraic laws govern social organization.
That's the core assumption.
Yeah.
And the foundational moment for this whole idea was in structural anthropology, driven by Claude Lévi-Strauss's work on kinship.
Right. Lévi-Strauss was obsessed with the idea that social institutions weren't random, that they were systems of communication and exchange, and that they operated according to algebraic rules.
His great challenge was the incest taboo. He argued it wasn't really a biological rule, but the first cultural rule. It was designed to force different family groups to exchange women, the rule being, you have to marry outside your kin group. He needed mathematical proof that these complex exchange rules formed a closed, logical system.
And to get it, he went to one of the greatest mathematicians of the 20th century, André Weil.
Yes, from the famous Bourbaki group. And Weil took on the notoriously complex Murgeon marriage system from Arnhem Land in Australia. The Murgeon Society was organized into 8 distinct marriage classes or sections.
And the rules were incredibly strict and cyclical.
Very strict. A man from Section A must marry a woman from Section B, and their children automatically belong to Section C, and so on, in a cycle through all 8 sections. They were ensuring the maximum distribution of social and genetic links across the entire community over generations.
So how did Weil analyze this?
He treated the 8 marriage classes as the elements in a set. And he treated the marriage rules, like you must marry your father's sister's daughter, as the binary operation, the permutation function. And then he just tested the system against the four group axioms.
Did it satisfy them? Did the Mergen system satisfy closure and invertibility?
It did. Weil proved that the system satisfied closure. Any combination of marriage rules always resulted in an existing valid class. It was associative, it had an identity, and crucially, it was invertible. You could track the lineage backward algebraically.
So he proved Levi-Strauss's hypothesis. This so-called primitive social system was operating on a sophisticated algebraic algorithm.
More than that, Weil proved that the Mergen system was isomorphic to a finite abelian group. You can model it as the cyclic group of order 8.
And because it was abelian or commutative.
The system was perfectly balanced and symmetric. It was a rigorous mathematical structure that was ensuring a maximal perfectly balanced distribution of links throughout the population.
But not all social systems are so balanced. What happens when the social structure is non-commutative?
Exactly. Later on, researchers applied this same group-theoretic method to other tribes, like the people of Ambrim in Vanuatu, and they found that the Ambrim kinship structure was fundamentally non-abelian.
So what does that mean socially? If the abelian Mergen system means social exchange is balanced, what does the non-abelian nature of the Ambrim system imply?
It implies that the order of relationships matters, and that leads to inherent asymmetry in social power and the flow of resources. For instance, in an abelian system, the relationship you have with your mother's brother is structurally symmetric to the one you have with your father's sister.
But not in the Ambrim system.
No. In the non-abelian Ambrim system, the algebra itself dictates different rights, different duties, and different social distances between, say, a maternal cross-cousin and a paternal cross-cousin. The group structure itself dictates hierarchy and power asymmetry, based purely on the non-commutativity of the relational operations.
That is profound. The simple mathematical question of whether A dot B equals B dot A dictates the flow of power in a society. Okay, let's move from these ideal kinship rules to modern empirical social interactions. This brings us to social network analysis, or SNA.
This is where we move from Levi-Strauss's ideal structures to Harrison White's work in the 70s. He was focused on taking these huge, messy social graphs, like a corporate network or a political network, and partitioning them into manageable, meaningful categories.
He wasn't looking for individuals. He was looking for interchangeable algebraic positions in the network.
Exactly. The whole goal of his method, called block modeling, is to simplify a network of thousands of unique people into maybe 8 or 10 general roles. And this relies entirely on the group-theoretic concept of equivalence.
And there are different levels of this. Let's start with the most intuitive one, structural equivalence.
Structural equivalence is the most restrictive, the most strict. Two people are structurally equivalent if they have identical ties to the exact same third parties. They're perfectly interchangeable. If you swap actor A and actor B in the network diagram, nothing changes.
So, like, two identical entry-level workers who both report only to the same supervisor and have no other connections.
Perfect example. Yeah. It's useful for identifying redundancy. But as you can imagine, social reality is rarely that simple. A general in an army can't be structurally equivalent to another general because they lead different divisions with different specific soldiers, even if their roles seem identical.
So you need a more abstract definition of sameness.
Right, which brings us to the next level, automorphic equivalence. This is rooted in the automorphism group of the network graph itself.
An automorphism being a shuffling of the graph that preserves all the connections.
Precisely. It's an isomorphism of the graph onto itself. A complete rearrangement of the nodes that leaves the pattern of connections identical. Two people are automorphically equivalent if there is an automorphism that maps actor A perfectly onto actor B.
Let's use that classic example of the corporate franchise.
Okay, take two identical McDonald's franchises in the same city. Manager 1 and Manager 2 are automorphically equivalent. Manager 1 deals with employee set X, Manager 2 deals with employee set Y. So they are not structurally equivalent.
Right, they're connected to different people.
But if you swap the entire subnet of Store 1, the manager, the employees, the suppliers, with the entire subnet of Store 2, the overarching corporate network remains unchanged. The two managers occupy structurally indistinguishable positions. Their role is the same.
And finally, the highest level of abstraction, which really gets at the idea of a social role.
That's regular equivalence. This is the most powerful and, for sociology, the most useful. Actors are regularly equivalent if they have the same types of ties to equivalent others.
So they don't have to connect to the same person or even an automorphically equivalent person.
No, they just need to connect to someone who holds the same kind of role they do.
So two different mothers in two completely different families. They don't know the same kids, but they both hold the mother relation to a node that holds the child role.
Yes. It abstracts away all individual identity to focus purely on the pattern of required action. The algebraic structure here lets you collapse a network of thousands of unique people into a small, meaningful set of generalized roles. It reveals the deep structure of the social system.
The rigor this brings is just incredible. Now let's go internal, into the architecture of the human mind itself, through the work of Jean Piaget.
Jean Piaget proposed that the development of human intelligence, specifically during the formal operational stage, which is when abstract reasoning kicks in during adolescence, involves the acquisition of a specific, defined algebraic structure.
He literally believed that the ability to think abstractly and logically was rooted in a mathematical operation set.
Yes, he argued that mature, complex thought is defined by its ability to achieve reversible equilibrium. For every operation the mind performs, it has to be able to perform a transformation that reverses it or compensates for it. And that required a group structure. He called it the INRC group.
Okay, so what are the four specific logical operations that make up this INRC group?
The four operations form a group that is isomorphic to the famous Klein-4 group, or K4. They are I for identity, N for negation, R for reciprocity, and C for correlativity.
Can you define those actions for us?
Sure. I, identity, is just leaving a logical proposition unchanged. N, negation, is the full inversion. If A is true, then not A is true. R, reciprocity, is compensating for an operation with an inverse operation on a different dimension, like adding a wheat to the other side of the scale to balance it.
Yeah.
And C, correlativity, is the inversion of both the subject and the prediction. It's often seen as a negation of the reciprocal.
And because they form a group, they have to satisfy all four axioms. How do they combine?
The Klein-4 group structure is very elegant because every element is its own inverse. Performing any operation twice gets you back to the identity. N.Tn equals I, R.T.R equals I, C.C equals I.
And combining any two of them gives you the third.
Yes. N.Tr gives you C, N.C gives you R, R.T gives you N. It's a perfectly closed, self-contained logical system.
And Piaget argued that this specific, tightly constrained algebraic structure is what defines the mature thinking mind.
That was his claim. He argued that before this stage, a child's thinking is linear and irreversible. They can learn to add, but they see subtraction as a totally new, separate rule, not as the inverse of addition. But the adolescent, by acquiring the INRC group structure, gains the ability to see every operation, like negation, as being intrinsically linked to a compensatory operation, like reciprocity. This is what allows the mind to juggle multiple variables to hypothesize, to achieve cognitive flexibility. And that structure is directly mapped onto the group's architecture.
That is the ultimate structuralist claim. The very architecture of abstract thought is dictated by the symmetry requirements of a four-element group.
Indeed. It suggests that logic isn't just learned language, but an inherent algebraic capability of the mind.
Okay, for our last section, let's look at collective decision-making, where group structure often acts as a constraint, forcing outcomes, starting with economics and game theory.
Right. In game theory, we often deal with games that possess some form of symmetry. A symmetric game is defined as one where the payoff depends only on the strategy you choose, not on who you are. If player A and player B switch roles but use the same strategies, their payoffs also just switch.
And the existence of a stable solution, the Nash equilibrium, often depends on using that symmetry.
That's exactly what John Nash did. He used the game's symmetry group, the permutation group that acts on the players, to prove a crucial theorem in his work. Every finite symmetric game has at least one symmetric Nash equilibrium.
So if the game itself is invariant when you swap the players, the solution must also reflect that invariance.
It's a necessity dictated by the structure. The solution space has to share the symmetry of the underlying problem. By recognizing the game's symmetry group, Nash could prove that a stable point must exist that conforms to that invariance. It dramatically simplifies the search for a rational outcome.
But in political science, this idea of enforcing symmetry leads not to a stable solution, but to a famous paradox, Arrow's impossibility theorem.
Arrow's theorem is all about trying to find a fair way to combine individual preferences into a single, consistent social ranking. And the paradox arises because when you impose what seem like perfectly fair, rational symmetry constraints on the system, you find that no such consistent ranking is possible, except through dictatorship.
Let's focus on the two symmetry requirements that make the problem impossible: anonymity and neutrality.
Anonymity is a group theoretic constraint. It demands that the voting rule must be invariant under any permutation of the voters. Swapping voter 1's ballot with voter 2's ballot cannot change the final result.
It enforces perfect symmetry among the people voting.
And neutrality enforces symmetry among the choices. It requires the voting rule to be invariant under any permutation of the candidates. If everyone prefers candidate A over candidate B and we just swap their names on the ballot, then the social choice should just reflect that same reversal.
And Ayer's theorem basically says that when you impose these two powerful forms of symmetry and variance under voter swapping and invariance under candidate swapping, the geometry of the preference space becomes too constrained to allow for a consistent outcome.
That's right. Recent mathematical work using the representation theory of the symmetric group shows that the impossibility is a direct consequence of the imposed symmetry. The constraints eliminate all possibilities except for one that radically breaks one of the initial symmetry conditions.
By introducing a dictator.
By introducing a dictator who, by definition, is not interchangeable with any other voter. The symmetry must be broken to get a result.
Wow. We've gone from the 8 gluons in the strong force, defined by SU3, to the non-commutative kinship rules of the Ambrym, the symmetry requirements that break voting systems. Let's step back and synthesize all this. What does this massive range of application tell us about the fundamental nature of reality?
It solidifies the central, unifying idea of structuralism across all domains, that the algebraic relationships are always more fundamental than the elements they govern. It doesn't matter if you're dealing with quantum fields or social networks. The identity of the element is secondary. Its role in the system of transformation is primary.
So the electron is defined by its role as a representation of a group. The marriage partner is defined by their role as an element in a transformation function.
And this structuralist perspective helps us draw that crucial distinction we talked about earlier between the two great domains we explored.
The difference between the ontological and the heuristic.
In physics, group theory is ontological. The SU3 symmetry isn't a model. It's a physical requirement of nature. This is why the great conservation laws, conservation of energy, momentum, charge, aren't just arbitrary rules we discovered. They are, as Noether's theorem proved, the necessary consequences of invariance under the appropriate Lie groups. The group is the structure of reality.
But in the social sciences, the application is different. It's a model.
It's heuristic. The Merton system, for instance, only approximates a perfect abelian group. Human behavior introduces errors and deviations. But the power of the model is its ability to capture the ideal normative structure, the underlying logic that organizes the chaos, the logic that the society strives to maintain, even if individuals sometimes fail.
So whether the group dictates the law of nature itself or whether it provides a powerful, rigorous mirror reflecting the deep logic of our own culture, group theory provides the universal lens.
It is the universal grammar of structure. It shows us that the complexity of the natural world and the complexity of the social world are not two separate things, but are parallel expressions of the same deep structural logic. A logic governed by those four simple axioms: closure, associativity, identity, and invertibility. It's the definition of order that persists through constant change.
And so now, you possess the mathematical lens to look past the surface identity of objects, whether they're quarks or crystals or roles in a corporate hierarchy, and to understand the underlying structure that is defined entirely by their interactions and their potential transformations. So for our final thought, we established that the non-abelian structure of the Ambrym kinship system implies an asymmetry in their social power, all because the order of relationships matters. If we apply that exact same logic to modern economic organizations, which are inherently non-commutative because the order of managerial decisions matters profoundly, doing A then B is very rarely the same as doing B then A, what does the algebraic structure of a global corporation's social network tell us about its fundamental weaknesses or its inevitable paradoxes, simply because its transformation group is non-abelian? We leave you to consider what happens when a system's required function demands asymmetry, and what that truly means for the people who have to operate within it.